There is a potentially interesting difference between molecular clouds as they existed at the time of reionization and present-day molecular clouds. And there's a point of difference between them that I want to draw to your attention. Now I'm going to just take a model of a cloud and explore its consequences as a function of the metallicity of the gas. Well, let me see. Oh, here we are. So I'm going to argue that early stars are metal poor, with a metallicity Z, which is very much less than the solar metallicity. And so presumably, I might argue, are the clouds in which these early stars were born. I'm going to take a chemistry and ask what it does to the composition of the clouds. So I'm assuming a chemistry that is ionization driven at a rate which I'll take to be 10 to the minus 15 seconds to the minus 1. The cloud has a density of 10 to the 4th per cubic centimeter and a temperature of 200 degrees Kelvin. And I'm going to assume that the grains and the heavy element abundances are proportional to the metallicity. Here I show as a function of the metallicity the distribution of hydrogen between atoms and molecules. And we see that at very low metallicities that the H2 we know is made by radiative processes. Of radiative attachment followed by associative detachment. That's what occurs in the early universe in the absence of grains. But for high metallicities, it's entirely different. The molecule is made on the surface of grains, as in the present-day molecular clouds. There is a chemistry initiated. With the presence of molecular hydrogen, there's a chemistry can take place. And the ionization, for example, is swept from being just the original protons to metals like carbon plus, sulfur plus, and silicon plus, and so on. So here is a demonstration of what the results of calculations. And as I say, the ionization now appears in the form of the ionized heavy elements. So here's some of the chemistry that goes on. These reactions were first written down actually by Bill Klemperer and Eric Herbst of the chemistry department here. So what they show is that this is just an extract from a very large number of reactions. The Charles transfer drives the H plus to O plus. O plus reacts with a series of abstraction reactions with H2 to make OH plus, to make H2O plus, and also, as it happens, to make H3O plus. They then, the sequence then terminates by dissociative recombination. I have here H2O plus an electron produces OH plus H. So those are the reactions that produce OH. Now from OH, reactions with carbon and carbon plus make CO. So this is the essential chemistry that makes carbon monoxide and the hydroxyl radical. Now, with the presence of H2, there's a substantial chemistry can occur, but I just isolated out the results as a function now of metallicity, function of the fractional abundances of the carbon and the oxygen. These are the consequences. So what the calculation shows is that that for high Z, for high metallicity, clouds today, carbon monoxide is the most abundant molecule, other than, of course, H2. But at low Z, and it seems possibly interesting, that's the point of my talk in any case, at low Z, OH is the most abundant molecule, not CO. The hydroxyl radical, and the reason is clear, is that for low metallicity, the abundances of C and O are small, and C and O requires one to bring together two heavy elements, whereas to make OH you only need one. And of course, atomic oxygen might be expected to be a significant component of the gas. So that's actually my talk. I just wanted to draw to your attention that for low metallicity, which is presumably applies to population 2 stars, the main component is not carbon monoxide, it's OH. So I thank you for your attention.
There's considerable interest in finding CO at high redshift. A lot of experimental work on this right now. It's very popular. And some success in finding CO. Is there OH line that we can move for? Sub-millimeter line? Is there an analogous line to the rotational transitions of CO that are so popular that we could use to look for OH?
Well, yes.
Summarize the question.
The question was, well, the comment was firstly that there have been attempts to detect carbon monoxide, early carbon monoxide, and the question is, are there similar transitions by which one might hope to detect OH? I mean, it's the question that this analysis leads to is to ask, what is the likelihood? At first sight, the answer seems to be yes. That OH is a molecule just like CO. Of course, it's a hydride, so all the frequencies are much larger. Whether they're in an observable region or not, I guess what I would say, well, that is the question that now, if you accept the argument, then that's the question that now needs to be addressed.
In this context, it's important to also mention that star-forming regions in our galaxy and nearby galaxies, that there are OH masers you can see in the radio. And so these are easier to increase, but they have a much larger brightness dimension than you expect from thermal equilibrium. And if OH is abundant, perhaps there are OH masers also in the early galaxies.
Yes.
It'd be easier to see.
But I mean, because some conclusions seem to be sensitive to the assumptions, but it's not because it's the difference between bringing two particles together, heavy particles, and one. It seems to me the conclusion must be right, even if some of the underlying assumptions, the model cloud that I used, are not really appropriate.
Two quick questions. What's the importance of H3 plus chemistry in this model? And the second question is, hydrogen fluoride has a tighter binding energy than OH, and there have been Herschel observations which suggest that HF is more abundant than CO, and I assume probably more abundant than OH. Did you include any fluorine chemistry in this?
Yes, but the fluorine chemistry is very simple. I mean, all the fluorine is in the form of HF. The question was.
So abundance-wise, do you expect the HF would be more abundant than OH or CO?
Yeah, well, it's a very simple question. It's a simple answer. Unfortunately, I don't know what it is. But I will know. But it's I mean, all the fluorine is in the form of HF. There's you have to compare the fluorine abundance with the oxygen abundance.
We can do that offline.
Yeah.
But what about H3 plus chemistry?
Oh, that's a significant source as well. Reacting with oxygen, it feeds into the OH plus sequence. So it's I mean, I just showed the processes, some of the processes that lead to, say, carbon monoxide. But there's we actually used a much more elaborate chemistry. There was someone else. Phil. The question was how much cooling results from other processes, in particular from the fine structure excitation of atomic oxygen. That, by the way, was why we took a temperature of 200 degrees. That's the energy associated with the fine structure transitions of oxygen. We had to really do calculations, and if you believe the arguments, now's the time to actually do calculations to make to actually predict the temperature, calculate the temperature, rather than just assuming it's 200 degrees.